Okay, so we'll work through the entire practice final. If you guys have any questions along the way, don't hesitate to raise your hand and ask, okay? This is just to make sure everybody is comfortable with all the material we've covered. And that's that, okay? So if anything doesn't make sense, just raise your hand, and I'll do my best to answer. Okay, so I'm going to just copy bits from the practice final, put them over on here, and then I'll post all of these slides online as well. Okay, so you'll have the answers to study from as well. Hope your studying's going well, and okay. Can you guys read this? Do I need to make this larger? Okay, maybe is that better? I don't know, let's see. Okay. Okay, so we're asking, are any conditions violated? Okay, so we'll just go through our 3 conditions and just check to see if any are violated. So we will have random and independent. Okay, and what we have is that it says they're randomly selected here, and they are randomly selected here. Okay. All right, so not violated. The subjects are selected randomly. And then we have the large sample, or I'm sorry, big population condition. Okay, so the relevant population would be everyone who could be exposed to lights. So this is a huge population, right? This is like millions or billions of people. Okay, so our population is definitely big enough, okay? Okay, and then lastly we have the large sample condition. Okay, so here we have 2 samples. Okay, we have one sample of 80, so this is the bright lights. We have 80 people, and what we have is 20 complain of headaches. So how many people don't have headaches then? 60, okay? Okay, so 20 is bigger than 10, and 60 is also bigger than 10. So both are larger than 10. So we're good there. Okay, over here we have the less bright lights. We have a total of 90 people, and 12 have headaches, which means how many don't? 78 have no headaches. Okay, so 12 is bigger than or equal to 10, and 78 is bigger than or equal to 10. So again, these are both greater than or equal to 10. Okay, so this condition is met. Okay, so all 3 of these conditions are met. So we have no conditions are violated. Next problem. Can I flip to the next slide? Yep. All right, so we got a researcher wants to make a confidence interval for how common a disease is. He finds 300 randomly selected subjects and finds 2% have the disease. Okay, so we'll check them. Okay, so we got random and independent condition, and this is met because it says randomly selected subjects. Okay, we have a big population. So what would our population be in this case? 300. No, not 300. Population is everyone. Everyone, either, you know, in the world or whatever, okay? Because we want to know how common a disease is, right? So this is everyone who could even be exposed to the disease, yeah.
But if it doesn't say where the disease is, like, it doesn't say if it's coming from a city or a country or the world.
Okay. I mean, yeah, you know, if somebody asks, like, what is the prevalence of HIV, then that, you know, if nobody specifies, like, what's the prevalence of HIV in Los Angeles versus that just somebody says, what's the prevalence of this disease, you kind of just have to assume, like, we're talking about everyone, right? The world. So
you don't specifically say it, I'm assuming it's the world.
yeah, if potentially, yeah. If it doesn't specifically say, then you can kind of assume the world, unless it says like a school or something like that. Okay, so everyone in the world. So this is huge. So big, you know, definitely big enough. Okay. Okay, and then we have a large sample condition. So how large is our sample? Sample has 300 people, okay? And then, so we have to count how many, quote, successes and failures we have, okay? Here we're not given counts, and the last time it said we had counts, right? It said like 20 people had headaches or 12 people had headaches. Over here it doesn't say how many people have the disease. Instead it says 2%, okay? So what is 2% of 300? This is going to be 0.02 times 300, or this is our n times p, and we get 6. Okay, so this is the quote number of successes, and then which means 294 people, quote, failures. And I don't like these labels, but that's just what they are. So we have 6 yeses and 294 no's, okay? This one's bigger than 10, but this one is not bigger than 10, okay? Or not greater than or equal to 10, okay? So, so our sample is not large enough. And so this condition is violated. Okay, I'm gonna keep chugging along here. Okay. The student has to conduct a survey for a school project. He goes around the school campus and interviews people he meets. He finds that 100 people, he finds data from 100 people and finds that 45 of them answered yes to his questions. Okay, so we've got random and independent. We've got big population, and we have large sample. Okay. Is our random and independent condition met? No. Okay. Not met because he's just walking around. Okay. Not selected randomly. Okay. The big population, here it doesn't really specify how how big the population is. The population seems to be people who attend the school. Okay, so the population is probably maybe the school or maybe the world. It's hard to tell. Okay, and it's not specified. So this one we don't know. Okay, large sample, 45 yeses, 55 nos. Okay, so these are both bigger than 10. So if it were a random sample, it would be large enough. But so definitely random condition is violated. And then big population, we don't know. Okay? May or may not be violated. For the final exam, I've made sure all of these questions are unambiguous regarding whether something is violated or not violated. Okay, so I know this one's a little not the best question because whether the big population condition is violated or not is ambiguous. So it's hard to say. But on the final, I read through them and I made sure that all of my questions are unambiguous regarding these conditions. Okay. So that's question 3. Okay, and then lastly, okay, so we have the random condition. Okay, and then it says it selects them randomly, so this is met. And then we've got big population. And here our population would be the company, which has 800 people. Our sample has 100 people. Okay, so our population is not 10 times the sample. Okay, so this condition is violated. All right, and as far as the large sample condition, we have no information about this.
On the final, will there only be one answer to each question, or will more than one apply?
Yeah, on the final, I've made it so only one condition is violated at a time. Okay. All right, we go down checking these conditions. All right, good. All right, then let's start working through these problems. Okay, it says a farm wants to test 2 different diets for their cows to see which diet causes more weight gain. They randomly select 10 cows to give diet 1 and select 12 cows for diet 2. After 2 weeks on diet 1, the 10 cows gained an average of 15.2, standard deviation of 4.1. After 2 weeks on diet 2, blah, 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 blah. Okay, the following questions refer to a 95% confidence interval for the difference in the average weight gain. Diet 1 minus diet 2. Okay, so what do we have? We have a confidence interval. And are we dealing with means or proportions, and do we have 1 sample or 2? 2 samples, and we're dealing with means. I guess not equals. Okay, so 2 sample means. So as far as the data that we need, we have sample 1, sample 2. So I'm going to have N1 x bar 1, and s1. And n2, x bar 2, and s2. All right, shall we go through and label these parts here? Okay, 10 cows give diet 1, so what's this number? N1, okay? 12 cows for diet 2. That's going to be N2. X bar 1, the 10 cows gained an average of 15.2 pounds with a standard deviation of 4.1. X bar 2 is going to be 12.6 with a standard deviation of 3.4. Okay, so I've labeled all of the parts here. Okay, and so you can either use the kind of the study guide or the practice formula sheet. Okay, so here we've got, you know, and I apologize, I've made a mistake. This says proportions. It should say means here, and this should say means. Okay, but I think it should make sense. Okay, so we've got confidence interval, means, 2 samples. This is the formula we're going to use. Or you can go through each of these things, you know, what's the center, what's the critical value, and all of this, okay? So what will the center of the interval be? All right, so that's going to be x bar 1 minus x bar 2, okay, so number 5. So I've got 15.2 minus 12.6. So I get 2.6. Okay, for a 95% confidence interval, what value will you use for t star? Okay, so our degrees of freedom is going to be n minus 1. How many degrees of freedom do I have? So I've got my n1 is the smaller n, so I'm going to have 9 degrees of freedom. And I've got 95% confidence. So that leads to what? T star equal 2.262. Okay. 7, what's our standard error? So our standard error, S1 squared over N1 plus S2 squared over N2. Okay, so this is going to equal, just plugging in a bunch of numbers. I'm going to pull up the calculator. All right, 4.1 squared over 10 plus 3.4 squared over 12. I get 1.626. Okay, create a 95% confidence interval for the difference in the average weight gain. So this is x bar 1 minus x bar 2 plus or minus t star times our standard error. So I have 2.6 plus or minus 2.262 times 1.626. Okay, so 2 times 2.262, got 3.678. So on my low end, and on the high end, that is equal to, okay, so here my answer is negative 1.078 to 6.278. Yes?
So I ended up getting
It should be fine. I mean, so it's multiple choice, okay? So the final's going to be multiple choice. I've made hard answer choices, but I'm not evil in the answer choices, okay? So I'm not going to have like one option being 6.28 and another option being 6.29 and another option being 6.30, okay? It'll be something like, you'll probably have 6.28 versus 4 versus 6.6 or something like that, okay? Where it should be, your answer should be very close to one of my answer choices, maybe off by rounding error, or maybe the last digit is off by 1 or something, or 1 or 2. It should be fairly close, okay? And I don't have, I won't have none of the above on there, okay? So it's not going to be like, your answer choices are 6.29 and 6.3 versus none of the above or something, okay? So I feel like I've been fair with the answer choices. Yes?
For question number 6,
Uh-huh.
I do know that the formula for getting our divisor to is n minus 1.
Yes.
But can you remind me which n we're taking?
So we've got 10 and we have 12. And whenever you have two n's, you use the smaller of them.
The smaller.
Yeah. Okay. Yes.
So is there a specific indicator that's going to tell us if it's going to be mean or proportion? Like I know that you were just able to say that it's mean. Is there something?
There will not. I will not say anything on the test about whether it's mean or proportion. You got to read through the question, and you got to see words like average, standard deviation that tell us we're dealing with means. Okay. You can the key, if you're dealing with a numeric variable, it's means. If you're dealing with a categorical variable, it's proportions, okay? And our variable here is weight gain, okay? So weight gain is a numeric variable, so that's why we're dealing with means, okay? And if you read the thing and you're not sure, is this numeric or categorical, you got to keep reading the problem and look for keywords like average and standard deviation, which will tell you you're dealing with a numeric variable. Yeah.
You're going from quiz 5 to 8.
What's that?
You're going from quiz 5 to 8, like the final would be like linear like that?
So the final, I would say the practice final is a good reflection of what the final looks like. Okay, so strong emphasis on statistical inference, a handful of questions about checking conditions, and then kind of a few, a small handful of older questions. Yeah, Armin.
Will there be anything on regression?
No. I mean,
Thank you.
other than just like like a conceptual definition-based thing, but no calculations with regression or things like that. Yeah.
Are you going to have a similar format, for example, like this problem has questions that are correlated to this problem?
Yes. So they're all of the things will have kind of like a statement, a paragraph with information, and then there's going to be, here I have like 5 or 6 questions related to it. On the final, it'll probably be like 4. Okay. Okay, so based on my confidence interval, do you conclude that there's a difference in the average weight gain? What do we say? No, and why do we say no?
Because when you find your t-value and go onto your chart, your t-value is going to be between 0.1 and 0.05, so it's going to be greater than all those.
Okay, so we actually don't even need to find a t-value here, okay? What we can do is we can look at our confidence interval, and we see that our confidence interval contains 0, okay? It's not entirely positive, it's not entirely negative, okay? So we write our confidence interval contains 0. So we do not have evidence that that there's a that there is a difference in average weight gain. Okay, And then as far as number 10 goes, if we made a 90% confidence interval rather than a 95% confidence interval, what happens? The 90% confidence interval will be narrower than the 95% confidence interval. Yes?
Yeah, with that question, I thought it was like a trick question, but I was like, if you reduce it, then the range is gonna be smaller.
Correct.
That's it, right?
Yeah, that's it. Yeah. If you're lowering your confidence, you can get a tighter range of where you think it's going to be, but the trade-off is you're less confident about that. Okay, so you can give more precise answers, but you're not going to be as confident about your answer. Okay. Keep going. Okay, we're going to the ruler and stick factory. It's my favorite place to go. Here it says the yardsticks it produces are supposed to be exactly 3 feet long. You measure a random sample of 40 yardsticks, find that the average length is 3.02 feet with a standard deviation of 0.03. Is this evidence that the machine is producing yardsticks that are too long? Okay, and we go through the questions and it talks about things like hypothesis tests and p-values. Okay, so from looking, just kind of glancing ahead to seeing what the questions are about, we can see we're talking about a hypothesis test here. Okay, because we see things like, you know, p-value, hypothesis test. All right, and so now the question is, are we dealing with means or are we dealing with proportions? And do we have one sample or 2 samples? Yeah, we've got means, okay, and we can tell because we're talking about the length of a yardstick, so we're dealing with means. Okay, and then as we read it, it just says you have a random sample of 40 yardsticks, and it doesn't mention another sample or anything like that. So we have one sample. Okay, so with hypothesis tests and means and one sample, we can start answering these questions. All right. So is this going to be a one-sided or a two-sided test? Where do we go to look for that? Okay, we look at the question that says, is this evidence that the machine is producing yardsticks that are too long? Okay, so the fact that it says too long here is going to indicate that this is what? A one-sided test, okay? Okay, and what this tells us is that for our hypotheses, here, let's come down here for number 12. Our hypotheses, we've got a null hypothesis and an alternative hypothesis. When we have a hypothesis test for a mean with one sample, the null is just mu is equal to some number, okay? Or, you know, you can go to the study guide, and over here it talks about for one sample mean, the mu is just equal to some number, okay? And then so we have an equal sign and it's going to have a mu. What's the number that our mu is supposed to be equal to? 3, okay? So we want this equal to 3, and we want to know, is it too long? So it's going to be, is the average of our yardsticks produced longer than 3 yards? Okay, so these are going to be our hypotheses. Okay, so for number 13, we're going to calculate our test statistic. Okay, so let's list off the data that we have. We've got one sample, so we're just going to have an n, an x bar, and an s. What's our n? What's our sample size? We have 40 yardsticks. Our x bar, the average of our sample is 3.02, and our standard deviation is 0.03. Okay, so we've got these numbers. These are n, x bar, and s. Okay, and so our test statistic, okay, we're going to figure out our standard error. 0.03 divided by the square root of 40. And I get 0.00474. Okay, and our test statistic, t is going to be x bar minus mu sub 0 divided by our standard error. What's our x bar? X bar is 3.02. What is the value that shows up? Oops. What's the value that shows up in our null hypothesis? 3, right? And we're going to divide by our standard error of 0.00474. Okay, so let's do this. 3.02 minus 3 divided by 0.00474. And I get 4.216. Okay, so this is my test statistic, 4.216. How many degrees of freedom do I have? 39. 40 minus 1. I've got 39 degrees of freedom. But when I go to the table, I don't see 39 degrees of freedom. So we round down, okay? And we're going to use, not in table, round down, use 30 degrees of freedom, okay? So we're going to go to our table, 30 degrees of freedom, and we're going to see where does our test statistic 4.216 go, okay? So 4.216 is beyond the last number in 30 degrees of freedom, 3.385. Okay, so what does this tell us? Yeah, so this means our tail area is going to be less than our column heading of 0.001. Okay, so our p-value, because it's a one-sided test, we don't need to bother doubling it. So our p-value is also less than 0.001. Okay, so the p-value is less than 0.001. Okay, so number 15, our p-value is less than alpha, which tells us we reject the null hypothesis. Okay, what does it mean to reject the null hypothesis? Does it mean we have evidence or we do not have evidence?
We have it.
Yeah, so we say we have evidence. Here, actually, I should write this up here. We have evidence that the machine produces sticks that are too long. Okay, so that's number 15. And then number 16 is if the conclusion you just made was wrong, what kind of mistake did you make? Yeah, so what we did, our decision was to reject the null hypothesis. Okay, if that was wrong, if the decision was wrong, that means the null hypothesis was true. Okay, so if the null hypothesis was true, then, so this is going to be a type 1 error. catch up on copying these down. Okay. Keep on keeping on. All right, so we got 17 through 22. And here it says, researchers believe that 14% of the population is left-handed, and a local school decided to see if their students have a different proportion of left-handed people. The school has a total of 1,500 students, and they randomly select 90 students for the study. And they find that 15 of them are left-handed. Is this evidence that the proportion of left-handed students at the school is different from the population proportion? Okay. All right. Okay, so what do we have here? Are we dealing with a confidence interval or a hypothesis test? Confidence interval, right? It says confidence interval and talks about confidence. So here we're dealing with a confidence interval. And are we dealing with proportions or means? Proportions. One sample or two? One sample. Okay. Why don't we list off the data that we have? What do we have? What is our sample size? 90 students. How many people are left-handed in our sample? 15. What's our p hat? 15 divided by 90, so 0.1667. Okay? And that's actually our answer to number 17. P hat is 15 over 90, 0.1667. Okay, if we're going to make a 90% confidence interval, what critical value z star do we use? 1.645. This is just from values that we must know, right? Sounded like a dog. Okay, and then when making a confidence interval, what is the standard error? So for number 19, our standard error is given by this formula. We can just either go to the formula here, or we can look at the study guide and we can see, okay, with the standard error, it's going to be p hat when dealing with one proportion, not p0. So 0.1667 times 1 minus 0.1667 divided by 90, and we take the square root there. And when I punch this in, I get 0.0393. So number 20, the center of our interval is going to just be p hat, which is 0.1667. And number 21, we're going to make a confidence interval. So we're going to have p hat plus or minus our z star times the standard error. So here I get, what do I get? 1.645 times 0.0393, 0.0646, or 0.64 something. Okay. Okay, so on the high and on the low, .2313. And on the low, we just do this minus 0.1021. Okay, so our intervals goes from 0.1021 to 0.2313. So far, so good? Creating the confidence interval? Yes.
I guess I got lost somewhere. You have 1.6 or 0.1667
Yes.
times 0.16 or 1.645.
Oh, I'm sorry. This should be plus or minus. I'm sorry. That's a plus or minus. Plus or minus 1.645 times 0.0393. Okay, so this is my high end and my low end. Yeah. Questions? We're good? Okay, so then based on our interval, is this evidence that the proportion at the school is different from the nation? So what's the national proportion? 14%. Okay, so nation is 14%. Is 14% a plausible value based on our interval? Yes. Okay, so 14% is inside our interval. So it is a plausible value. Okay, therefore, we do not have evidence that the proportion of left-handed students at our school is different. Did you have a question? Where does the 14% come from? That comes from the problem that says 14% of the population is left-handed, and so we want to know, is the proportion different from the population proportion? Okay, so there's this number 14%. This is somehow known to be the national percentage, and we want to know, okay, well, we're gonna survey our school, okay, and we're gonna try to see, is our school different from the nation? Is there a question back there, Jacob? Change your mind. Okay. You can change it back to Armin.
So usually, like, we compare to alpha. Is it safe to just compare to the 14%?
So here we are not comparing to alpha. Alpha only comes into play when it's a hypothesis test. Okay? So here we're doing a confidence interval. So with a confidence interval, there's no alpha involved. Confidence interval, you're just looking at what numbers are included inside the confidence interval. Okay? So the values that are inside the confidence interval are all plausible values. So when it's for like one for one mean, 14 or one proportion, 14% is a plausible proportion. And that's why we can't say our school is different from 14%, because based on our confidence interval, 14% is a plausible value for our school's proportion. Yeah.
Because it falls in our interval.
Because it falls in our interval, exactly. Okay. Because 14% is in between 0.1021 in 0.2313. Okay, let's look at this one. Here we have a hypothesis test. Okay, we're talking about Starburst candies and Jolly Ranchers. A bag of Starburst have 80 pieces and 12 of them are cherry flavored, and a bag of Jolly Ranchers contains 70 pieces and 14 of them are cherry flavored. Okay, and we want to know, do they have a different proportion of cherry flavored candies? Okay, and it looks like we're going to do a hypothesis test, so I'll go ahead and write that here, hypothesis test. And the question here is, do we have one sample or two samples? Are we dealing with means or proportions? Okay, we got proportions because we're talking about the flavor of candy. It's a categorical variable. Cherry candy is yes or no. Proportions, and then we have two samples. It says Starburst and Jolly Ranchers. Okay. All right. So for number 23, our null hypothesis is going to be what? P1 minus P2 equal to 0, or P1 equal to P2. Those are equivalent ways of saying the same thing. What would the alternative hypothesis be? Okay, because yeah, here it says different. So we're going to have P1 minus P2 not equal to 0. Right? What's P hat when we're talking about hypothesis test for proportions? Yeah. Yes. Why is it 0? Oh, okay. So we have, there's two forms of writing the hypotheses, okay? We could also write, these would also be valid. P1 is equal to P2, and an alternative would be that P1 does not equal to P2, okay? Correct, because it says different. Okay, and so just from simple algebra, if I subtract P2 from this side, I would get a 0 over here, and then on the left-hand side, I would get P1 minus P2. So I'm just doing algebra to go from here to here or from here to here. So these two things are saying the exact same thing. Okay, so number 24, what's P hat? P hat is x1 plus x2 over n1 plus n2, right? Okay, well, let's go through and list off our data. We have sample 1, and we have sample 2. Sample 1 will be our starburst. We have n1, x1, and p hat 1. And we have n1, x2, n2, x2, and p hat 2. Okay, what's n1? N1 is 80. x1 is 12. And our p hat 1 will be 12 divided by 80.15. n2 is 70. x2 is 14. P hat 2 is 14 over 70.2. Okay, and so what I'm going to have here, x1 is 12, x2 is 14, n1 is 80, n2 is 70. I've got 26 over 150. My p hat is 0.1733. Okay, 25. Okay, let's figure out our standard error. Standard error is going to be the square root of p hat times 1 minus p hat. times 1 over n1 plus 1 over n2. So I'm just plugging in the values here. We're going to get some kind of number here. Get the square root of that. 0.0619. 0.6195. Okay, my z-score is going to be p hat 1 minus p hat 2 over the standard error. So I got 0.15 minus 0.2 divided by 0.06195. And if I do that, I get negative negative 0.81. So far, so good?
So just one more time to be sure, so when the variables are categorical, then we're doing proportion hypothesis, and when they're numerical, it's mean.
Correct. If the variables are categorical, it's proportions. If it's numeric, means, okay? And whether it's a hypothesis test or confidence interval depends on what questions are being asked. But other than that, yes.
Safety applies even if it's a confidence interval.
Yeah, it'll, you know, so, you know, here in the test, I mean, in the questions, we're seeing hypothesis tests and p-values. That's how we know it's a hypothesis test, okay? If the question talks about confidence level and things like that, then you'll know it's a confidence interval. But whether you're doing proportions or means depends on whether it's categorical or numeric. And so yes, categorical variable, always proportions. Numeric variable, always means. Yeah.
Instead of trying to figure out what it is, you can just look at it to see if it's asking for p hat, and then you know it's proportion.
No, p hat, okay. Yeah, so p hat will be proportions, yes, yes. If it asks p hat, then that's a clear indicator that it's proportions, yeah.
Rather than trying to figure out if it's numeric or categorical.
Yeah, I mean, I guess for me, that's my base instinct to see if it's numerical, categorical. But, you know, for other students, you know, maybe other clues are better. And so, yeah, p hat will be a good clue that it's categorical or proportions. If somewhere in the thing it talks about standard deviation, then that's going to be for means. Okay? Okay, let's see. Okay, so that's our z-score. So here I got, I guess I'll write these answers. Okay, what's the p-value? Okay, so what do we do to get the p-value when our z-score is negative 0.81? Okay, so we're going to go to our table, and we're going to look up the area to the left or to the right. Area to the left, because it's negative, right? We want the area away from 0, okay? So the tail area is equal to the area away from 0. So this is going to be, I look up negative 0.81, and the number I get is 0.2090, okay? So negative 0.81 is 0.2090. So this is my tail, and is my tail the p-value, or do I double my tail to get the p-value? I double. How do I know to double? Because the alternative has a not equal sign, okay? So HA has a not equal sign, so we double the tail to get our p-value. Okay, so our p-value is going to equal 0.419, or I'm sorry, 418. All right, and so number 27, perform a hypothesis test. What is the conclusion we make? Yeah, so our p-value is greater than alpha. This means we do not reject the null. what does it mean that we didn't reject the null?
We kept the original.
We do not have that.
Yeah, it means we don't have evidence that there's a different proportion of cherry flavored candies between Jolly Ranchers and Starburst. It's a very important question that we're answering here, okay? So we do not have evidence that there is a difference in the proportion of cherry candies. When did Skittles switch over to green apple instead of lime? That was like, it's a sad day. All right.
And then right after that, Trident made a lemon flavored gum.
Who would eat that? I don't know. Okay. Well, anyway.
It's actually really good.
Is it actually really good? Okay.
I like it.
All right. I'll take that as a recommendation then. Oh, I'm sorry. I flipped over to the next slide, but go back. Okay, just give me a second. Let me go ahead and just get this copied over, and I'll go back. You got it. Okay. Okay, are we good now? Not yet? Yes? Just another second. Are we good? Okay. Let's keep. Oh wait, no, that's not what. Shoot. Where am I? That's here we are. No. Okay. Yes, that's the. This was like our first day of class. Do you remember that? No? Oh, man. Why do we study statistics? What? To help us understand the world? Allows us to make make conclusions from limited data, okay? It's the best. All right. Okay. Well, I love it. I love it. This is my dream job, all right? You can tell? Well, good. Hypothesis testing, and are we dealing with means or proportions here? We're dealing with means. How do we know? It's in the question. It talks about means, and it's got standard deviation and things like that. Okay, so we got means, and we have, what, 2 samples, right? And then, okay, so we're going to perform a one-sided hypothesis test, okay? And that's because it says improves reaction time. What should the hypotheses be? Okay, so what does it mean to improve your reaction time? So does it take you longer or less time to respond to something? Okay, so you got to think about what these things mean, okay? So improved reaction time It's not tricky. It's just you gotta think, right? So improved your test score. That means your score went up, right? Improved your improved on performance might mean like you got fewer mistakes or something like that. So you just have to think, what does it mean to improve? So improved reaction time means less time to react. Okay. All right, so keeping that in mind, number 28, our hypotheses. Our null hypothesis will be that mu1 is equal to mu2, and our alternative will be that if mu1 is the group with caffeine and mu2 has no caffeine, so this one has caffeine and this one says no caffeine, right? 0 milligrams of caffeine means no caffeine. Do we expect the mu1 to be greater or less than mu2? Less, okay. We expect the caffeine group to have a smaller reaction time than the no caffeine group. Okay? So you can't just say like, oh, improves, more is better or something, okay? You gotta just pause and think for a second. Maybe it's different. Okay. What's the observed difference in means? What is that? Okay, well, maybe we'll list off our data that we have. Okay, so our data, we have sample 1. Okay, sample 1 will be the caffeine group. Sample 2 will be no caffeine. I'm thinking of just powering through to get out a little bit early. If you got to excuse yourself to use the restroom or something, you can excuse yourself, okay? All right, so sample 1, we have 30 people. N1 is 30. X bar 1 is 580. And the standard deviation S1 is 110. Okay? What's this number 300? Does this do anything? No. Okay? It's just in there to indicate whether you have caffeine or no caffeine. Okay? N2, we have 25 people. Our reaction time, X bar 2, 640. And the standard deviation, S2, is 130. Okay, so our observed difference in means is going to be X bar 1 minus X bar 2. We have 580 minus 640. We have negative 60 milliseconds. Okay, number 30. We got to figure this out. Our test statistic, okay? So our standard error is going to first be 110 squared over 30 plus 130 squared over 25. Okay. When you do all the math, I'm getting 32.85 for standard error. Our test statistic T is going to be X bar 1 minus X bar 2 over the standard error. So I have 580 minus 640 divided by 32.85. I'm getting negative 1.826. Okay. We got to get a p-value. So how many degrees of freedom do I have? I've got two n's, so we're going to have 24 degrees of freedom, right? 20 degrees of freedom is n minus 1. We use the smaller n, so this will be 25 minus 1. I've got 24 degrees of freedom. I'm going to look up 1.826, okay? We just ignored the negative, but knowing that the table is going to have the area to the left. So we're going to go 24 degrees of freedom, and we're looking up 1.826. So we get our tail area is in between these two numbers, I mean, sorry, 1.826 is in between these two numbers, 1.711 and 2.064. So our tail area is going to be between 0.05 and 0.025. So 1.826 is between 1.711 and 2.064. So our tail is between 0.050 and 0.025. Okay? Do I leave my tail area as is, or do I double my tail area to get the p-value? Leave as is, right? Because it's a one-sided test, okay? So one-sided test, we leave it as is. Leave tail as is. So our p-value is between 0.050 and 0.025. So we write this, we'll say 0.025 is less than our p-value, which is less than 0.05. Okay? All right, if our alpha is 0.05, how does our p-value compare to alpha? It's less than that, okay? Because right here it says p-value is between 0.025 and 0.05, so it has to be less than 0.05. So 32, our p-value is less than alpha, so we will reject the null hypothesis. Okay? And that means we have evidence that caffeine improves reaction time. I'm running out of room for number 33. I'm going to just cram number 33 in here. Okay. Number 33, so in number 32 we chose to reject the null. If that was a mistake, if we mistakenly rejected the null, that is what kind of error? Type 1. Okay, so mistakenly rejecting the null is a type 1 error. Oops. Yes.
What was the p-value again, 31?
The p-value is between 0.025 and 0.05. So when we look up our test statistic of 1.826, we see that it's in between the columns for 1.711 and 2.064. So it's in between these two numbers, so that means our tail area has to be between these two numbers. It's not too bad, right? So. We're just sad that it's all going to be over next week, right? So sad. All right, 34 through 39. Okay, we're looking at the police department and the fire department, and we're going to see how many have the proportion of minority employees, and we're going to do a hypothesis test. Okay, are we dealing with means or proportions? Okay, we got proportions. Okay, well, because we have p hat here, but also whether someone is a minority or not, that's a categorical variable. And how many samples do we have? we have two samples. We've got the fire department and the police department. Okay, let's go ahead and list off our data. We have the police and we have the fire department, and we're going to have N1 and X1 and a P hat 1, N2, X2, and a P hat 2. How many people selected from the police department? 200 at random. 80 were minorities, so we're going to do 80 over 200. We get 0.4. At the fire department, 200 people randomly selected. 50 were minorities, so we're going to do 50 divided by 200. 0.25. Okay, what are the appropriate hypotheses? The null hypothesis will be P1 is equal to P2. The alternative, P1, and it says different proportions, so we're going to have a not equal to P2. Number 35, what is P hat? P hat is going to be x1 plus x2 over n1 plus n2. So I've got 80 plus 50 divided by 200 plus 200. So this gives me 130 over 400. What is that? 0.325. So our test statistic, we're going to have to calculate our standard error first. It's going to be 0.325 times 1 minus 0.325 times 1 over 80, 1 over 200 plus 1 over 200. And if I did this correctly, I'm getting 0.04684 for my standard error. So my z-score is going to be p hat 1 minus p hat 2 divided by our standard error. I get 0.4 minus 0.25 divided by 0.04684, and I get 3.20 as my z-score. Okay, so now we're going to look this up to get our p-value. How do I do this? I'm going to look up z is equal to 3.20. And do I want the area to the left or to the right? To the right this time, okay? Because I've got a not equal sign, right? So the alternative has a not equal, so our p-value will be equal to 2 times the tail area. So our tail area, because z is positive, is the area to the right. Is the area away from 0. So we're going to look up 1 minus, and we look up 3.20 in the reference tables. 3.20 is 0.9993, so I have 0.1 minus 0.9993, so I have 0.0007. This is my tail area. My p-value is going to be double that, so my p-value is equal to 2 times 0.0007, 0.0014. That is my p-value. Okay, 38. What is the conclusion we would make? We would reject the null hypothesis. This means we have evidence that the proportion of minorities are different, that the proportions of minorities are different for the police and fire departments. Okay, and then number 39 is, in the context of this problem, what does it mean to commit a type 1 error? Okay, so type 1 error is the null is true, but we reject it. But we conclude otherwise. So in the context of this problem, the null being true means the proportion of minority employees is the same at both at the fire and police departments. Okay, so this would mean, in truth, both police department and fire department have the same proportion of minority employees. Okay, but our decision is that we believe they are different. Okay, but we conclude the proportions are different. Okay, that's what it means to commit a type 1 error in the context of this problem. And I guess everybody knows I'm not taking attendance. Well, not everybody. You guys have stuck around. But there's like 25 of you. You just have my gratitude for sticking around. I appreciate you guys. I'll miss you guys. Aww. Oh yes, my favorite problem, the potato bags. Okay. So, do you ever wonder about these things? Maybe I'm the only one. I always wonder, like, how do they know? Like, because you just buy like this giant thing and it says like 10-pound bag of potatoes, and you're like, how close to 10 pounds is this? Like, I'm not gonna. Huh? Yeah.
There's a scale there.
I know, they have the scale, yeah. So I put them on and I'm like, oh, it's pretty close. I mean, but it's like, I'm not gonna go through the entire store. Excuse me, sir, what are you doing? I'm just making sure I'm getting the right amount of potatoes. So. I just watched the trailer to an upcoming movie called Sausage Party. Have you guys heard of this? No. Okay, it's gonna be like a rated R cartoon, animated film, and it's just about like I don't know why I'm telling you this. The food at the grocery store think it's their destiny to go home, and they don't realize that people that the food gets eaten, and so there's like. They're like, oh, I was chosen, and then they get home, and then the person starts peeling the potato, and then the other food looks on in horror, like, oh my, like they're like cursing, like what is going on, and they're like trying to run away. I'm sure it's going to be a high quality movie here. Okay. Okay, are we dealing here? It says center of the interval, stuff like confidence. So we got a confidence interval going on here. And we have means because we're dealing with weights of potato bags, and we've got one sample going on here. Okay. So we're going to go through, let's list off the data that we have. We've got one sample, so this is easy. We got n and we're going to look at 10 bags. We've got x bar, the sample, 5.2, and our standard deviation is 0.3. Okay? So number one, our degrees of freedom is going to just be n minus 1. I've got 9 degrees of freedom. Okay? As far as 41 goes, what value goes in the center of our interval? So our interval looks like x bar plus or minus t star times our standard error. And our standard error is s over the square root of n. Okay, so what value goes in the center? X bar. So number 41, x bar goes in the middle. We're going to have 5.2. 42, what is the value of our standard error? S over the square root of n. So we're going to have 0.3 divided by the square root of 10. I'm getting 0.0949. Okay, and our confidence interval will be 5.2 plus or minus. Okay, we're going to have to look up t star. Okay, so t star, we have 9 degrees of freedom, 95% confidence. So I go to my table, 9 degrees of freedom, 90% confidence, 2.262. I think we saw this guy earlier today. 2.262 times our standard error of 0.0949. So I got 5.2 plus or minus 0.2146, okay, or 0.215. We'll just round it off there. So on the high, I have 5.415, and on the low, I have 5.2 minus 0.215, 4.985. Okay. Question?
Yeah, the center of the interval,
Uh-huh.
did you get
I'm using my x bar. So the center of the interval is always going to be, you know, when you look at the equation or the formula for a confidence interval, the center is always the part that comes before the plus or minus, okay? The center is the part before the plus or minus. Okay. All right, and so the question is this evidence that the bags at the grocery store have a mean weight different from 5 pounds? So what is our answer? We're going to look at our interval. Our interval goes from 4.985 to 5.415. So for number 44, do we have evidence that it's different from 5 pounds? No, right? Because 5 pounds is inside our interval. Okay, so this means 5 pounds is a plausible value. So we do not have evidence that the mean weight is different from 5 pounds. Okay? Question? You're good. Everyone's good? Great. Okay. Last one. Last one of these, what do you call it? These thingamajiggies. Inference problems. I hope this is helpful for you guys. Going over all this. Okay. All right. A fair die should land showing a number 4 1/6 of the time. You roll a die 100 times and you count how many times it lands on 4, and it lands as the number 4 20 times. Is this evidence that the proportion it lands 4 is different from 1/6? Okay, so we're going to do a hypothesis test because it says write the appropriate hypotheses. And are we dealing with means or proportions? Proportions, because we're talking about the proportion it should land on the number 4, and we've got one sample. Okay, so let's just list off our data. How many times do we roll the die? 100. How many times did it land on 4? 20. So our p hat is 20 over 100, or 0.2. Okay, so number 45, what is our hypotheses? So we've got the null and the alternative. They're both going to be about p. The null is going to be that p is equal to 1/6. It should be equal to 1/6. And then the alternative is that, is it different? So is it different from 1/6? Okay. I put it in fractional form. If you want to turn it to decimal, that's fine. But it's multiple choice. So if you see it presented as fractions, I hope that doesn't throw anyone off. Fractions and proportions, exactly the same thing, right? Okay, the sample proportion is our p hat, which is going to be 20 over 100, which is 0.2. Straightforward enough. Okay, 47. When performing a hypothesis test, what is the standard deviation of your sampling distribution? This is just a fancy way of saying, what is the standard error? Okay, that's the definition of the standard error. It's the sampling distribution of it's the standard deviation of the sampling distribution. That's the definition of the standard error. So here our standard error is going to be the square root of p0 times 1 minus p0 over n. What is p0? 1/6, right? It's not 0.2. It's 1/6. So I've got 1/6 times 1 minus 1/6 divided by 100. Okay, so you can enter it as 1/6 in your calculator or something, or turn it into decimals if you want. It shouldn't make a big difference. So this is what I get for my standard error. When performing a hypothesis test, what is your test statistic? Okay, this is going to be z is equal to p hat minus p0 divided by our standard error. So I'm going to have 0.2 minus 1/6 divided by 0.03727. And when I do that, I get 0.89. Okay, so 49, I'm going to get my p-value. My p-value, because it has a not equal sign, and the alternative will be 2 times the tail area. So is my tail area, do I go to the left or to the right? I go to the right because I've got a positive 0.89, right? So my tail is area to the right of 0.89. So looking that up, whoops. 0.8133, so I'm going to do 1 minus 0.8133. I get 0.1867. My p-value will be 2 times that, which is 0.3734. And this means we do not reject the null hypothesis. We do not have evidence that our dice, or our die, rolls the number 4 at a proportion different from 1/6. Yes. For the tail area?
Yeah.
Okay, so the rule is if the alternative has a greater than sign, you take the area to the right. If the alternative has a less than sign, you take the area to the left. If the alternative has a not equal, you take the tail area and you multiply it by 2. Tail area is the area to the right if the test statistic is positive. Tail area is the area to the left if the test statistic is negative. Is that good? Okay. So in our case, we have a positive test statistic, so our tail area is to the right. Good? Good, good, okay. All right, so then, just this stuff. What? Is this a lot of stuff? I feel like I'm making everything so, all right. Major League Baseball wishes to conduct a survey of its players. Instead of trying to create a list of all the players from all their teams, MLB decides to randomly select 4 of their 30 baseball teams. Cluster sampling. All right, good job. Okay. Company wants, or if, okay, what would it have to say if it was going to be stratified sampling? So for stratified sampling, they would make sure that they surveyed someone from every single team, right? They would make sure that every team is represented, okay? If they said, they're going to make sure that someone, that they've sampled this amount of people from every single team, that would be stratified sampling. But with cluster sampling, it's like, oh, we got all these groups, we're just going to pick a few of them. Okay. Wants to survey its employees. They take its master list of everyone in the company and randomly selects 100 of them for the survey. SRS, great. Okay. Toll Bridge wants to survey the drivers. They decide to stop every 10th car. Systematic. Easy, I tell you, easy. Huh?
Just these 3.
Yeah. Okay, a bar chart is used for what kind of data? A bar chart is for categorical data. Okay? I'm going to just say these out loud for you guys. Here, maybe I'll pause it. Okay, in a normal model, approximately what proportion of data are within 2 standard deviations of the mean? 95%. And we remember the rest of our empirical rule. 1 standard deviation goes to what? 68. 2 for 95. And 3 standard deviations? 99. Huh? When did you learn this? Chapter 6. Chapter 6.
Okay,
Yeah.
1 is for 68%.
Yeah, 1 is 68%. 2 standard deviations, 95%. 3 standard deviations, 99.7. I know we covered this. Okay, the intercept in linear regression would be our predicted value when x has what value? When x is 0, right? All right, if the probability of A and B are happening together is 0, then that means A and B are... They are mutually exclusive. What's independent?
When they rely on each other.
No, when they don't rely on it. When the outcome of one has no influence on the other, right? If two things are mutually exclusive, can they be independent?
No.
Yes, no, maybe? No, they can't. They can't. Okay. Okay, for a quantitative, oh, this is another fancy word for numeric. For a numeric variable, if there is only one peak in the histogram, how do we describe the shape? Unimodal. Unimodal. Which measure of center is not influenced by outliers? Not influenced. Whoa, sorry.
Don't put that question. Not a good sign.
Which measure of center is not heavily influenced by outliers? Right. Okay, we learned two measures of center. What were they? The mean and the median. Okay. All right. So which one is influenced by outliers? Which one's not influenced by outliers? The median is not. Okay. The median is not influenced by extreme outliers. Okay, so we'll end there.